Welcome back. Till the last module, we discussed stationary distribution and steady state behavior of countable state Markov chains using renewal theory. Right, so we used renewal reward theory to interpret the steady state probability pi I as 1 over TII, right, which is the expected recurrence time. We also used Blackwell's theorem to prove that Pijn converges to pi j if you have an irreducible aperiodic positive recurrent Markov chain. Now, all this is perfectly valid. What we have done so far is perfectly valid. However, it makes heavy use of renewal theory, right? Now, one might argue that is renewal theory really required, right? If it's valid to use it, we have studied renewal theory, but you may argue that, hey, so this I don't know any renewal theory. Suppose can you help me learn Markov chains? It turns out that you can derive some of these results, some of the key results about stationary distribution and steady state probability and all that without using renewal theory at all. All right, we can just use direct elementary approach and derive some of these fundamental results about stationary distribution and steady state behavior of Markov chains. Okay, so that is something I want to do today. Not in great detail, but I will just point out how the arguments go. This part is from the book by Grimet and Sterzeker's book on probability and random processes, 3rd edition, section 6.4, which is, this is a lovely book, and this section is a good exposition on the stationary distribution and renewal without renewal theory, right? Okay, so my agenda for today is to roughly tell you how the stationary distribution can be constructed explicitly without using any renewal theory, and how the convergence to steady state can be proved. All right. So, I am given, let us say, given DTMC which is irreducible and recurrent. I want to prove that the existence of a stationary distribution. I want to prove the existence of a stationary measure, okay. And in the case of positive recurrence, the stationary measure will be a stationary distribution. I will tell you what I mean by a stationary measure. It is a counting measure that we will introduce. And also for an aperiodic, if the DTMC is also aperiodic. So, what I mean is that it is irreducible, recurrent and aperiodic, okay, positive, recurrent and aperiodic. Then I want to show that there is a convergence to steady state. That is what I want to do. So, I want to show that limit n tending to infinity Pij n is equal to pi j, all right. This is for all j in S, for all I in S and for all j in S, okay. So, this is convergence to steady state. So, remember for the first for the existence and the uniqueness of stationary measure and all that, we have used for the stationary distribution we used renewal reward, and for the second we used Blackwell's theorem. I want to do it without using any of these renewal theory arguments, all right. Okay, suppose, so you are given a DTMC, okay, you are given a recurrent irreducible DTMC. Okay. So I am going to say, let us say I fix j recurrent. So I am just going to fix a recurrent state j. Okay. So that is my Markov chain running in time. Okay. Let us say I start at j. Let us say given x naught equals j. Let us say I have a j which is a recurrent state and I start the Markov chain at state j. Okay. Then this is a recurrent state, so I have to return to state j at some point, and I will in fact with probability 1 I will keep returning to state j infinitely many times. Earlier we said that these consecutive return times constitute a renewal process, but I do not want to. I am going to pretend that I know nothing about renewal theory at all, okay, in this lecture. So what I am going to do is you take any other state I, okay. Let me mark it differently. So let me say that I am hitting state I in these places, okay, at these times. I am going to say Ri. So I am going to just consider this interval between two consecutive visits to j. So I start at j and I look at the first return to j, and I used to call this tjj, right. So I will keep the notation, okay, but I will not use any renewal terminology, okay. I am going to define Ri as the number of visits to state I. So state I is in the same class, okay, state I is in the same class as j. Number of visits to state I before return to j given x naught equals j, okay. So this is some number, right. So earlier we used to say Ri is some kind of a random variable, right. We said this is some expected reward inside a renewal interval and all that, but forget all that, it is just a random variable at this point, okay. And I am going to say I am going to call rho I of j defined as expected Ri, which is the expected number of visits to I given that I started at j, right. So it is the expected number of visits to I before I come to j given that I started at j, okay. So this I will define for I am fixing a state j, and this is defined for the other states s, right, including state j, right. Now I am going to use this rho I of j as some kind of a counting measure, okay. So I am going to argue that there is a stationary measure can be stationary measure and eventually a stationary distribution can be constructed using these rho ij's, okay. So to be a little more precise, maybe I should define Ri as sum over I is equal to 1 to tjj indicator xi, maybe I should say n is equal to 1 to tjj, indicator xn is equal to I, alright. So it is the number of times I am in state I before this stopping time tjj, right. Or I can also write this as sum over n equals 1 to infinity indicator xn equals I intersection n less than or equal to tjj, alright. This is my expected this is Ri, okay. I can write then rho ij as the expectation of all this, right, expected all that given x naught equals j, right. Which is just sum over n equals 1 to infinity, expectation of sum over 1 equals indicator xn equals I, indicator sorry, intersection n less than or equal to tjj. This I can take the expectation inside because all the terms are non-negative, right. So, this just becomes n equals 1 to infinity probability that xn, sorry, all this given x naught equals j, beg your pardon, x naught equals j, right. Xn is equal to I and n less than or equal to tjj given x naught equals j. Okay. So, this is my rho ij, rho I of j. Okay. So, now my claim is that this rho I of j, which is the expected number of visits to state I between two successive returns to j, is some kind of a stationary measure in the sense that it satisfies the balance equations, right. See, this rho I j will turn out to be a number, right. I am going to argue that this is a stationary measure. So, let me also define the vector rho of j as rho 1 of j, rho 2 of j and all that, okay, over all the states. Okay. So, this is a vector which contains all the rho I of j as you run over I. Okay. So, I am going to make a few claims now. Claims. First claim is that rho j of j equals 1. Okay. So, this is the expected number of visits to state j between the two visits to j, right, and one of the final return to j, you count the last return, right. So, in fact, you return to j when you return to j, right. So, that is the only time you count this particular reward. So, if you put that I am saying reward, but it is not, I mean I am not really in the, I mean in the renewal world we used to think of it as the reward. You basically collect 1 unit of reward when you return to j, right, but it's here we are just counting and that is all right. So, we get 1 expected unit of reward, right. So, if you look at in fact rj will be equal to 1 in this, right. The number of times you visit j between successive returns to j. So, that will be equal to 1. Okay. This is claim 1. Claim 2 is that these rho I of j's are strictly between 0 and infinity. Okay. Claim 3 is that if you sum over all the states is rho I of j, you get expected tjj. Okay. So, the expected time between successive returns to j, remember that j is recurrent, right. So, you do have tjj is a random variable, right. What we are saying is that the expected tjj, the expectation of this random variable is equal to sum over all the states I of rho ij, okay, and this is true even if RHS is infinite. Okay. Of course, if tjj is a random variable, expected tjj could be finite or infinite. Expected tjj is finite, then we know that the chain is positive recurrent. Expected tj is infinite, the chain is null recurrent. right. But fact is that if you sum over the rho ij's, you get expected TJJ. This is true for both positive recurrent and null recurrent chains. And most important of all, this vector rho of j is a stationary measure, i.e., what we can show is that rho j p equals rho j, okay, where I am writing this pi p is equal to pi kind of a thing, except this pi I am writing, instead of pi I am writing rho j, and this rho j is not a probability distribution, okay, it's a stationary measure in the sense that it's stationary. You put rho j into p, you get another rho j, but it's not a distribution because it doesn't have to sum to 1, it doesn't sum to 1 in general, okay, it doesn't sum to 1 at all actually. Now, so okay, this is a shorthand for saying that maybe I should write this. See, this P need not be a matrix, right? P is infinite dimensional object here, right? So, I should really write rho I of j is equal to sum over k rho k of j pkj, right. Sorry, pki, I am sorry, pki, okay, rho k of j pki, okay. This is true for this is true for this stationary measure, so this rho j vector, okay. This is true for all I in S, okay. So, what I am claiming is that this rho ij, which I defined as the expected number of visits to state I between two successive visits to j, right. This rho ij satisfies rho jj equal to 1, which is reasonably clear because you have you basically return to j and that is the only time you count that. And the second claim is saying that this rho ij is strictly positive and strictly finite, okay. And third is saying that the sum over all I rho I of j is equal to expected time of return between j to j, expected tjj. And finally, which is the most important, it is saying that this rho j vector satisfies rho j of p, rho j p is equal to rho j, okay. We have to prove these, all right. I will indicate to you how this is proved, okay. So, now let us look at what the consequence is, right. If the DTMC is positive recurrent, i.e., if expected TJJ is finite, then if you take rho I of j over expected TJJ, can be interpreted as the stationary distribution of I, okay. So, that what I am saying is that if you call pi I as rho I of j over expected TJJ. So, I am saying, so this is finite, the denominator is finite, all right. So, this pi I will turn out to be something strictly positive, right, because rho I j is strictly non-zero and expected TJJ, because I have positive recurrence, is finite. So, rho I j over expected TJJ will be some positive number, right. Now this, if you take this pi I, okay, and you calculate it for all I and S, then clearly sum over pi I is equal to 1, right. That is because I am normalizing by expected TJJ, and that is because sum over rho I j over sum over rho I j is equal to expected TJJ, and I am normalizing by expected TJJ. So, sum over pi equal to 1. This is by due to 2, sorry, due to 3, right, which we haven't proven, and pi p is equal to pi from 4, property 4, right. So, further, if the DTMC is positive recurrent, I can take this rho I j and divide it by expected TJJ and interpret this as pi I, okay. Call this pi I, and this pi I will be a distribution over all the states in the sense that it sums to 1, and pi p will be equal to pi, it will be a stationary distribution, okay. Of course, if the Markov chain is null recurrent, you have the stationary measure rho I j, which still satisfies rho j p is equal to rho j, but you know, if you divide it by expected TJJ, you get all zeros, right. So, it does not sum to 1. So, this pi I will all be 0 and it is not really a distribution, okay. But so, even for a null recurrent chain, everything I have said before about rho I j still holds, except that you do not get a probability distribution over the states in a null recurrent case. In a positive recurrent case, you do get a distribution over the states, okay. So, what we are saying is that this is the steady state. So, pi I as the expected number of visits. So, the steady state probability of steady state distribution of state I has the interpretation as expected number of visits to I between successive returns to j divided by expected say expected recurrence time of j, which we are taking to be finite, right. So, this we already knew from renewal reward theory, right. In fact, we considered a reward process which gives a reward of 1 when you visit I, but the renewal process we considered was between visits to j, and we used renewal reward theory to come up with this. So, this is not surprising to us at all, because we have seen this using renewal theory, but all I am saying is that you can explicitly construct this pi like so, and from elementary principles, not using any renewal theory or anything, we can prove these claims 1, 2, 3 and 4, okay, which I have not done, which I will indicate how to do, okay. So, what I am saying is that you define this rho I j, and if your expected TJJ is finite, you divide rho I j by expected TJJ, and you call it that turns out to be pi I, which is your stationary distribution, which we already knew, right, from because we know renewal theory, okay, but we are constructing from first principles now.